Hi everybody, this is a video for my Intro Calc students, and this is lesson 1.3. This one's fairly straightforward. If you were thinking that 1.2 and 1.1 were kind of complicated, hopefully this one's a little bit easier. And the basic idea here is something called a one-sided limit. Now we kind of have talked about this a little bit. Recall that in lesson 1 we saw that a limit can exist at a point on a function where the function does not even actually exist. And the example that we can give of that is one like this one. Suppose I asked you for the limit as x approaches -1 of that function. Now, if we plug -1 in for x, right away you're dividing by 0, and you can't do that. So you should probably understand that the limit of the function might exist, even though the function itself doesn't exist. If f of x actually equaled x squared plus 7x plus 6 over x plus 1, then f of -1 does not exist, because again we'd be dividing by 0. So if we actually graph that, we looked at this a little bit the other day. Let me open up Desmos here. If we actually graph that, look what happens when, here it is. Notice that an x squared divided by an x leaves you with a linear function, especially since this x plus 1 is a factor of x squared plus 7x plus 6. And as I approach, let me just zoom in on it a bit. There we go. As I approach x is -1, you can see that I'm getting closer and closer to 5, 5.3, 5.2, 5.1. But when I actually get on that point of x is -1, I get undefined. In fact, if I was going to sketch a graph of this, and I left myself room to do that, if I sketch a graph of this, I should probably sketch it as the factored form of this, which is x plus 6, x plus 1 divided by x plus 1, which is just x plus 6. So that would be, 1, 2, 3, 4, 5, 6 for a y-intercept. 1, 2, 3, 4, 5, 6 for an x-intercept. And then at x is -1, actually draw a hole so that you have basically, it's supposed to be a straight line, and then there's a hole. Actually, I could maybe exaggerate it a little bit. There, hole, there we go. Definitely exaggerated, but you get the idea. You're supposed to draw it with a point that we would call a discontinuity. Right? The function is not continuous at that point. When you actually draw them on Desmos, remember the Desmos, you could actually zoom in quite a bit. So you can, no matter how much you zoom in on that point, it never actually draws it with the discontinuity until you actually highlight it, and or try to get yourself right on it. There it is, and then you can see that the point is a hole. So anyway, let's go back to home. If we were to graph, let me go back to the notes. If we were to graph that, we would find that there's we see that f of -1 does not exist, but as x approaches -1 from the left, y approaches, let's see, I've already forgotten what the actual number was. Let's see, as we approach -1, what is our x or y value? As you can see, well, we're approaching y is 5. So as you get closer and closer, you'll see that you get closer and closer to 5, so y approaches 5. And as x approaches -1 from the right, and that's what the that little symbol means from the left, and that little symbol means from the right. And again, let's see that on the graph. If we were approaching from the right, we get closer and closer and closer to 5. 0.5, -0.6, -0.7. We're at 5.3, 5.2, 5.1, and as you can see, we're definitely getting closer and closer to a y value of 5. So back to the notes. So as x approaches -1 from the left, as y approaches 5, and as x approaches -1 from the right, y also approaches 5. Therefore, the limit is 5, even though the function didn't even exist at that point. Okay, so we've seen that before, but we've also seen a slightly different situation. We also saw an example where a limit did not exist where the function didn't exist. And the example that we can think of was, I think it was the last example in the last lesson. The limit as x approaches 0 of 1 over x. The difference here is that when I draw that one, of course I get this function right here. Let me just go to Desmos again. And on that one, as I approach 0 from the left, as you can see, I start to get bigger and smaller and smaller. I head towards negative infinity. No matter how far I go to the right, I'm never actually going to touch the y-axis. I am going to just keep going down until, again, forever, till negative infinity. And the same thing is true if I approach it from the right. If I approach it from the right, notice I'd be heading up towards negative infinity. I'll never actually touch. So I'm not heading towards the same value as I approach from the left and right. So the way I wrote that is, the difference is that for the function I looked at in the last page, as x approached 1 from the left or the right, you approach the same value of y equals 5. But for this function, for f of x equals 1 over x, as you approach x equals 0 from the left, your y values go racing towards negative infinity, and from the right, they head to positive infinity. So, give you a sec to catch up to me. Feel free to pause the video if you want to jot this down, and I'm going a little bit too fast. So, I can conclude, in the case of our second example here, that a limit exists when the limit from the left is equal to the limit from the right. Or, to put that symbolically, we would say that if the limit as x approaches a from the left of some function is not equal to the limit as x approaches right of the same function, then the limit just in general as x approaches a for the function does not exist. But the opposite's true. If the limit from the left exists and it equals the limit from the right, then I would say the limit is some value L, which is the same value you get when you plug in the left and right. So this would be like the first example, and this would be like the second example. And again, if a function breaks up, there's a space between, there's a hole, the function seems to jump from one number to another, we call it discontinuous. So that's the rule, if you want to memorize it and remember it as a hard, fast rule. But it's a fairly easy thing for you to figure out. Here's a little blast from grade 11 past. There wasn't any of these on that grade 11 review sheet. There probably should have been, because this is one of the last things you did in grade 11 math. And I know some of you who had grade 11 math in semester 2, you might need a little refresher on this because you did this during COVID break. This is what we call a piecewise function. We've talked about these a little this year already. What it actually means is, here I'll graph it for you. It means that if I sketch a graph of this, I have a different function when x is less than 1 than I do when x is greater than 1, but together they make one complete function. So when x is, okay, let's go to 1 here. There's x is 1. Now before I hit, or up to and including this x value, I have the graph of y equals x squared. And y equals x squared, you should remember, is just a parabola that goes 1 over 1 up, 2 over 4 up. So it would do something like this. And of course, it goes to 1 over 1 up here. And that's where it ends, right? When you're equal to 1, you hit a solid dot there because that's as far as it goes. And then when you're greater than 1, you have the line y equals 3 minus x. And if you have the line y equals 3 minus x, rearrange that, and it's y equals negative x plus 3. So it's a line with a slope of negative 1 and a y-intercept of 3. Okay, well the y-intercept actually isn't going to exist, but let's just use it for a second to figure out where the point is. It has a slope of negative 1, so it goes down 1 over 1. And so starting right there, that is where the graph is going to start. And then again, down 1 over 1, down 1 over 1. It's going to look like this. And put arrows on that side. And there you go. It's going to look something like that. Now, why is this an open dot? Because notice that's a greater than. This, when x is 1, this isn't the function. When x is 1, this is the function. So it's a solid dot for there because it exists there, but it's an open dot there. And this is another good example of a discontinuous function. Just to show you, you can actually graph these on Desmos. You just have to kind of put them in a weird order. Desmos likes you to put the domain in first, and then using a full colon, two dots, one on top of the other, put the actual function. And then between the pieces of the function, you put a comma. So let me show you what that looks like. Oh, I haven't. Okay, let me just go over to here. I'll just make up a new one. Okay, I've already used F, G, H, and I. So this will be J. It doesn't really matter what letter you use. So this will be J of X, and it's going to equal the combination of from when X is less than or equal to 1, full colon, it is x squared. And there you go. There's that part of a parabola. It doesn't put a big solid dot there, but as you can see, you can rush right up to the end, and there it is, 1, 1, and then after that, you can't get any points. Then put a comma in there. Oops, you got to get off of the exponent. I just moved it with the cursor, if you're wondering, the arrow. And there we go, comma, and that tells it, okay, we weren't done yet. When x is greater than 1, we would like to have the function, so put a full colon, 3 minus x, and there we go. So there's what I just tried to draw on paper. That's not a bad diagram, reasonably speaking, considering I did it freehand. And there it is, and as you can see, that's clearly a discontinuity. So for this thing, I would say that this thing is discontinuous, that's one word, at the point x equals 1. And if you wanted the limit as x approaches 1 of f of x, you would say it does not exist. And you'd say that because the limit as you approach from this direction looks like it's heading towards 1, but then all of a sudden if you head this from this direction, it looks like the limit is heading towards 2. Right? And again, you can see that on the graph if you just drag a point and say, okay, I'm getting closer and closer and closer to 1, I'm getting closer to 1, then closer to 1, then all of a sudden it teleports and it's closer to 2. Right? And that is not something I can find a limit for. So, there's example 1. All right, let me go back here. Example 2. Suppose I wanted the limit as x approached 0 from the right of the square root of x. This is a more traditional one-sided limit. And the reason why this is a one-sided limit is because the other side of limit doesn't exist at all. Right? Because think about it, it would be ridiculous to even talk about this thing as a limit as x approaches 0 from the left, because if you graph this thing, the square root of x starts here, and then it goes 1 over, 1 up, 4 over would be 2 up. It would go like this, right? Because remember, why is there no graph over this way? Because you can't square root a negative. So you would just say that, oh, okay, I'll plug that in, plug in 0, and say that that's equal to the square root of 0, which equals 0. That limit exists because there's no limit on the other side to say that it doesn't exist. Does that make sense? Think of it as the limit as x approaches 0 of the square root of x is equal to 0 because the right limit says that it exists if you come at it from the right, and there is no left limit for it to argue with it. So let's put it that way. So that's example 2. Example 3, here's our old friend absolute value of x, and I oh, I actually made a graph for this one too. Here it is again, square root of x. And again, as I get closer and closer this way, my limit is 0. And of course, there's nothing over here. Oops, nothing over here. The next one's going to be the absolute value of x, which, remember, that's that guy, the big letter V, basically. And again, this is one of those things that you did in grade 11, and it was towards the end of the course. So maybe not such a bad thing that we're spending a little bit of time on it. So that's the absolute value graph. And think about that, the limit as x approaches 0. Well, as I go this way, so the limit as x approaches 0 from the right, I'm getting closer and closer to, of f of x, sorry. I'm getting closer and closer to 0. The limit as x approaches 0 from the left, coming from this direction, my hand just froze. Come back, hand, sorry. Let me backtrack here because I froze. As I look at what the x values, or what the y values are doing, sorry, as my x values get closer and closer to 0, as you can see, I'm approaching a y value of 0. And as my x values get closer and closer to 0 from the left, this way, again, f of x is going to equal 0. So the two left and right limits agree with each other. They both say 0. Therefore, the limit, oops, get ahead of myself here. The limit as x approaches 0 from both directions of the absolute value of x is equal to 0. Okay, so that's, again, analyzing this limit by using the left and right rule for limits. All right, so example 4. Let's end with another one of these piecewise functions. Okay, how about you pause the video here and sketch this. You can take out a piece of graph paper to sketch it if you want. And feel free to try it on Desmos as well. You should be able to kind of follow the way I did the last one. And so pause your video and give it a try. All right, did you make yourself a picture? All right, I'm going to try to make a picture as well. So determine if the limit exists as x approaches -1 and x approaches +1. So I'm going to make myself a sketch here. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Good enough, I think. All right. When x is greater than or equal to -1, I am the function minus x minus 2. So it has a y-intercept at -2, which again I may not actually have as part of my function. We'll see. So I have a y-intercept at -2, which I just put there, and then I have a slope of down 1 over 1. So down 1 over 1, and that means I can go up 1 and over 1, and then up 1 and over 1. Okay, so when x is less than or equal to -1, which starts here, this is my function. So this part here actually isn't even really part of the function, but it helped me make the graph. Okay, now between -1 and 1, according to this, I want to just be the line x. So between -1 and 1, I want to be the line x. So that would be actually here, and I'd go through that point, and I'd go through this point. But it's open dot here, because again, this is a less than, not an equal to. So open dot there. Now, I wouldn't draw an open dot there because there's already a solid dot there. So in other words, I don't really have to lift my pencil as I follow the graph this way. But here, I might have to lift my pencil. I'm leaving that as an open dot until I figure out what this thing does. Okay, y equals x squared minus 2x when x is bigger than or equal to 1. Okay, well, what happens when you plug 1 in there? 1 minus 2 is -1. Aha, so y is actually going to be down here. What happens when you plug in x is 2? You're going to get 4 minus 4 is 0. And what happens when you plug in 3 for x? And I'm sorry, my scale's kind of wonky there. But that'd be 9 minus 6 is 3. So 1, 2, 3 becomes 1, 2, 3. And as you can see, then we're actually curving up that way. It is a parabola that way. So let me make that a more clear open dot. Open dot. So there we go. Something like that. All right, did you try it on Desmos? Let's try it on Desmos, just to make sure that we know what we're doing. You should be able to do these. Okay, so let's get rid of that one and let's open a new one. I've already used FGH. I'll just use K of x equals. Okay, so to tell Desmos that you want to do a piecewise function, you open up the curly bracket. It's shift, the key beside the P button on a keyboard. And then plug in the domain first. So first the domain is x is less than or equal to -1. So you can get that by going x and then open up this for your actual menu, less than or equal to -1. Put a full colon, which is the shift beside the L key, and then that's -x minus 2 was the function there. There's that straight line part. Comma, that tells Desmos you're going to add another function to this. This function goes between -1 is less than x is less than 1. And in that domain, I want the function x. And there we go. There's that angle, that right angle that it kind of turned at. And notice again, it is continuous, right? There's no, I can trace this without lifting the pencil. Okay, and I wasn't quite done yet. And whoops, oh no, don't do that. Didn't mean to do that. Let's see. Toggle over, there we go. One more thing, so comma. I hate the fact that you kind of can't see the whole thing at once. It kind of just scrolls. That to me, I've told Desmos about this. I actually did get a conference in last year with the programmers at Desmos, and representing Manitoba schools was me and other places. And I said, hey, how about when you do the piecewise function, why actually can't you just type it in, making it look like this, which is the way you teach kids how to write it down? And they said they'd take it under advisement, but I haven't heard back from them. So anyway, what did I want to do? Oh yeah, I wanted to do when x is greater than or equal to a 1, I have the function x squared minus 2x. And there we go. Let's see, how close was that to my diagram? Pretty good. Not bad. And once again, as you can see, we have, this is not discontinuous here. At -1, we're approaching a y value of -1 from the left, and we're approaching a y value of -1 from the right. So to answer the question, which was, does the limit exist? Well, then I would say that here, the limit as x approaches 1 of f of x does exist, and it is in fact -1. Oh, sorry, that should be -1, not 1. My bad. But over here, the limit as x approaches 1 of f of x does not exist because it's discontinuous. F of 1 is a discontinuity. I hope I spelled that right. And that's about it. Check the blog and I'll have a little assignment for this section. And if you have any questions or concerns, message me.